Hello, my name is Father John Rickard. I'm pastor at Immaculate Conception Church in Omaha, Nebraska. And I have a presentation here called Syllogisms Made Easy. I want to get into examples as soon as I can, and therefore I'll just do some verbal remarks before we get into the method. Now, as you may know, the older system of doing syllogisms was really quite elaborate. It involved moods and figures, a lot of mnemonics, things like that, Barbara, accelerants, and so on. That medieval system is really very cumbersome. But then in 1880, John Venn did an approach using what he called Euler circles, but which we now call Venn diagrams, to do syllogisms. But I believe there is an even cleaner, simpler way to do these syllogisms. And in fact, that's why I want to do these examples, because once you see how these examples work, I hope that you'll agree that it's actually much easier. You can do these in your head faster and easier than doing even the Venn diagrams. So we need to talk about the various types of statements that we're going to look at and how those diagrams work. And then we'll talk about how the rules apply, what rules apply to these diagrams in working with them. And then we'll try to get into examples of syllogisms as soon as possible. So we do remember that there are four types of categorical statements: A, E, I, and O. And the A statement says, for example, that all S is P. The E statement says that no S is P. The I statement says some S is P, and the O statement says some S is not P. That should be familiar to you, and also we do have this whole thing about the square of opposition and these various operations we can do. I'm going to rush right on past that. When you see the way these diagrams work, you can actually go back and all that stuff will fall right in place. So I think it'll be more enlightening if we just rush headlong into how we do syllogisms, okay? So what are the diagrams that we're going to use for these statements? Well, for all S is P, we'll just do this. We'll have S here and we'll put P up here. So when we see a diagram like that, we interpret this diagram as saying all S is P. When I say no S is P, I'm going to say it in a little bit different way. It's actually called the obverse, but hopefully it's obvious that it's the same thing. We can say that all S is not P. Does that make sense? Is that clear? If I say no S is P, that is the same as saying all S is not P. And so the diagram there, again, will be very similar. So instead of saying all S is P, we'll say all S is not P, and we'll indicate that by an overbar. So overbar indicates not, okay? Some S is P, we get what I call a Y diagram. We'll draw like this. I'm going to put the empty set down here, has nothing in it. I've got S here and I've got P here. And now this point of intersection is really important, because what that says is I have something that is not empty. I have a real member, at least one member. Maybe more than one, maybe only one, but I have at least one member that is simultaneously S and P. So some S is P. And we can also see some P is S, that from the same diagram, right? So we could read that in either order. And hopefully, if this is making sense, you already see what the diagram for the O statement should be. Some S is not P would just be like that. So again, we don't have to worry too much about what this is, but we know something, that there is at least one individual that is simultaneously an S and a not P. Okay? So those are our four diagrams. And we just have a few simple rules for our diagrams. I'm going to need to make some space here. So one simple rule is on double negation. So for all categories, C. If we take not C, that's going to be the same as C. Double negation cancels out. That's standard. It just is a result of the kind of logic we're doing. Okay. That's one rule. Another rule is that if I have a diagram like this, whatever it may be, maybe it's a Y diagram, whatever, but the point I want to make is this, is if I have a category here and it's not category over here, the only thing that they can have in common, that C and not C can have in common, is the empty set. So no matter what this is allegedly supposed to be, if I flow down from here and here to where they meet, they can only meet in the empty set. Okay, I hope that makes sense. Nothing is simultaneously both a C and a not C. Again, that has to do with the meaning of our terms and with just kind of the metaphysical import of what we mean by terms here. Another operation that is helpful in these diagrams is what I call contraction. So if I get a diagram, and maybe I have other stuff in here, it doesn't matter. I can have other type stuff in here, it doesn't matter. But if I have a diagram like this with the same label here and here, I can actually just contract that diagram to a point. And so everything is equal to C. So in particular, if I get a diagram like this, let me maybe give another illustration. If I get a diagram like this, well then I've got A and A here, that's the same label, so I can contract this whole thing to a point, and I get A, and everything in between there is equal to it, so I get B as well. I hope that makes sense. I call this contraction. Okay. There's one more operation that is maybe a little bit trickier. It's very important. It's actually very simple when you think about it. Is if I start with a diagram like this, and I'm just going to use the letters A and B. I don't mean an A statement. I just mean two categories, A and B. This is going to be the contrapositive form. What I can do is I can flip these labels so B goes down and now A goes up, and then I negate them. Okay? And so it's really easy to see this. I guess I should have used different letters. If you're in Omaha, then you're in Nebraska, or all of Omaha is in Nebraska. And therefore, if you're not in Nebraska, then you're not in Omaha, right? So if all of A is contained in B, then if you are outside of B, then you absolutely must be outside of A. For if you were in A, then you would be back in B. Does that make sense? So this is just the contrapositive. So again, when we have a straight line diagram like this, we can flip labels and negate. And so the nice thing about this is we can do that trick again. And so now our A bar comes down here and gets another bar, and our B bar goes up and gets another bar. But again, I already said when I have a double bar, double negation, that takes me back to my original. And so sure enough, what we can see is that these two are really equivalent. They're really equivalent. The contrapositive is equivalent to the original assertion. Okay? I hope that makes sense. So as I mentioned a moment ago, we have all this terminology and technology about the square of opposition and obverse and converse and these various things like that. And I will leave that to you if you're interested in those. It's really a very straightforward exercise. But I think where this notation really, really shines is when we do syllogisms. And we're ready to do syllogisms. So it works like this. we make diagrams for our assumptions, then we try to find a single diagram that includes all of those assumptions. If that single diagram exists, then it shows that those assumptions are consistent, that they don't clash and contradict each other, right? Moreover, if that diagram, that model exists and is basically unique, then we can see what conclusion has to follow. So again, when we work the examples, I hope this will become very, very clear. So let us do, of course, the Barbara example. And I have to mention that St. Barbara is the patron saint of mathematicians. So that is very, very fitting for us to have as a first example. So Barbara. All M are P, all S are M, and therefore all S are P. That's our Barbara syllogism. How does that look in diagrams? Well, let's see, all M are P is this. And then all S are M is this. And so when we put these two together, well, S is below M. So usually when we do these, you may as well just copy one of the diagrams. S is below M, but then this one tells us that M is below P, so P has to be up here. So this is a model that has both of these assumptions, which is good. And if you have followed it so far, it's really the only way to put these together that respects the proper ordering. All M is P and all S is M. This is the only way you can arrange the dots on the line. But now what do we have? When we look at this diagram, what is that? That says all S is P. That's our conclusion. Okay, let's do another. How about I say no M is P, and I say all S is M. What do we get there? Well, I say no M is P. In other words, all M are not P. And all of the S's still belong to the M's there, like that. And again, when I put these two figures together, the only way to put them together is to have S here, M here, and not P up here. Just like the last example, I just have an extra bar over the P. That's the only difference. S has to go below M. M is below P bar, and we have that. So what do we have there? No S is P. Therefore, no S is P. Good? Okay. How about all M is P? And some M is S. Well, all M is P, and some M is S, so they have something in common more than the empty set. There is at least one member that is both an M and an S. And again, we put these together. Well, let's just copy this one as a starter. And again, P has to be above M. So the only place that it can go is up over here. And voila, look at that diagram right there. What is that? Some P is S. Therefore, some P P is S. Okay? So it all becomes very, very straightforward. Let's do an example where there is no conclusion. Let's do maybe an example or two where no conclusion follows, just to see what that looks like. And then what we'll do is we'll look at some examples that really are beyond what the standard textbook examples are for the categorical syllogism. So for example, how about I say some A is B and some B is C. Well, does anything follow from that? Not really. We can't say that some A has to be C because they just might miss each other. But let's see the way that works in the diagrams. When I say that some A is B, I have this. When I say that some B is C, I have this. Well, now, I can put those together so they are consistent, and I get something like this. So that is a consistent model. You can see that that includes this diagram right here, and this part includes this diagram right here. So this is a model where both of those assumptions are true. But what do A and C have in common? In this model, they have nothing in common. So we can't really conclude that there is any overlap between A and C. There could be. And the thing is, you could have a model like this, for example. Let's see. You could have a model, I think, I'm winging it here, so I hope I'm not off. You could have something like that. That's another model where A and C truly do have something in common. But you do have a model where they have nothing in common. So just in general, no conclusion will follow. How about another example where no conclusion follows? We'll say all dogs are quadrupeds. And let's say some animals are quadrupeds. So does any conclusion follow from that? No. And how can we see that? Well, again, all dogs are quadrupeds. So we've got our dogs and our quadrupeds, correct? And we also say that some animals are also quadrupeds. But now the question is, see, look at this. See, the Q is up here and it's over here. We're not going further in that direction. So the real question is, where does the D go? Well, the D could go here, or it could go here, or it could go here, or it could even go here. So this is a model, again, where you have a lot of liberty where the D can go. I'm sorry, I did not draw that correctly. I wanted to do this, sorry about that. I've got a model here where this relationship holds properly, and where, oops, I'm sorry, I forgot to copy mine, and where that some animals are quadrupeds holds. So that's also true. So both the assumptions are true. Sorry, I messed up my diagrams. I'll just erase my mistakes here and give you that. So this shows all dogs are quadrupeds, and some animals are quadrupeds. But again, what do A and D have in common in this model? They don't have anything in common. And so that gives an example, a couple of examples where no conclusion can be drawn. And so what you can actually do if you are a maniac on these things, you can go through and check and see that all of the valid syllogisms, you can check them one by one. I actually did do that at one point, so they're all good. But we're at a point where we basically have all the standard types of syllogisms down. Now what I want to do is go a little bit further and take you into some sort of non-standard type syllogisms, because the diagrams are very interesting here, and the conclusions I think are kind of neat. So here's an example of a syllogism, and this is number 6. I kind of blew it on the last problem. I didn't write the correct numbers and stuff, but hopefully I get a chance to do this one the right way. I say that all A is B, all C, I already blew it. All A is B. And I say all B is A. And so what conclusion follows from this? Well, again, if I say all A is B and all B is A, well then voila, I put these together and I've got a diagram like this. A, B, A. But then I use contraction, and that tells me that A is equal to B. And this is a type of argument that is used all the time in mathematics. Very common argument to show that two sets are equal. And obviously it's not one of the classical Aristotelian forms, because in the Aristotelian syllogism you have the subject, the middle term, and the predicate. They have to be 3 distinct things, and the middle term is shared and all that stuff. So the classic Aristotelian syllogism does not allow you to reach this conclusion. So the diagrams do. Now, there is one thing I hope you're wondering. You think, well, wait a minute. I started with this and then I added this on, but what if I do this? How about I do BAB? That's also a valid model, isn't it? It sure is. But then that just tells me that B is equal to A. So I contract it out again. So when I apply the contraction, it really does end up the same. There really is only one model, the model that concludes that these two sets are equal. So there's no contradiction here. So, and in fact, as I say, the diagrams do give us that conclusion, whereas the Aristotelian approach does not. Here's another one that I think is very interesting. How about I say, this is number 7. No dogs are cats. And how about I say some cats are not friendly. Well, these are two negative premises. The books will generally tell you that when you have two negative premises, you cannot draw a conclusion. Well, let's have a look. So, no dogs are cats. No dogs are cats. Remember that we deal with that in that form. All dogs are not cats. Okay? And some cats are not friendly. Okay. But now there's an interesting trick here. What we can do is we can do the contrapositive on that. Remember? You flip the labels and negate. Do you remember that? So I can say that that's equal to the system whereby I flip these labels and negate them, so the D goes up and gets a negative. The C comes down and gets a double negative, which takes it back to C. And then I have my diagram here as before with C and F. And now look at that. Now I've got a C here and C here. I can glue those two together, and that puts my D bar right there. So I hope I have just enough room here. Let me do that so it's not so confusing. So I've got a diagram like this. I've got Oh, did I forget a bar there? I did. Not friendly. There we go. And then I've got cats, and I have non-dogs. So again, should be pretty evident that this is a model that incorporates both of these assumptions, and that really the D bar has to go above the C. That's what this diagram says. And so that's where it goes. So again, we have a conclusion. What the conclusion is that some non-dogs are not friendly. So in fact, we have two negative premises, but we have a perfectly valid conclusion. Now, if you're still skeptical and you think, but wait a minute, all the books tell you two negative premises mean no conclusion. If you're still skeptical, you can actually do this in modern notation. You know, using like your for all and there exists and then good old Frege and all that stuff, using the modern way of doing this, it checks out. So this really is truly a valid inference here. The nice thing is that it falls out relatively easily from the diagrams. You don't have to memorize a bunch of rules and do a lot of conversions and stuff like that. If you diagram your assumptions correctly, you might say, okay, well, I got to flip this one or flip that one or whatever, but then you put them all together and there you are. So it's very simple by comparison, I think. And let's do one last example, and this is one where we're going to deal with multiple premises. And I hope I have enough room. In fact, let me do this. So this will be our last example. So all non-students are exempt from the test. So for example, maybe they're just auditing the logic class, so they don't have to take the test. And we say some non-exempt test taker failed. And let's say all who fail must retake the course. And for the fun of it, let's add one more. All who retake the course have to pay again. So here, instead of just two assumptions, we have four. Now, if you're already familiar with the Venn diagram approach, I hope you realize that this would be a nightmare, right? Because when you're dealing with the three categories, then you get the 8 areas and all that stuff. But when you're dealing with this many categories, it just becomes absolutely unwieldy. But let's see how it looks with our diagram. So all non-students are exempt from the test. So all non-students are exempt. Fair enough? If you're not a student, you're exempt. Maybe you're auditing, maybe you're babysitting, I don't know. Some non-exempt test taker failed. So someone who is not exempt did fail the course. Well, all those who fail must retake it. Maybe it's a required course. And finally, those who retake it have to pay again. And so now you can almost do this in your head, right? So all I have to do is, these line up nicely, these line up nicely, no problem there. Flip and negate, right? So I'm just going to flip this one right here. The E goes down and gets a bar. The S bar, comes up, gets another bar, which takes it back to S. So I'm going to do this right here. And now look at it. I can put these two together, and these two together, and these two together. It's pretty obvious they have to go that way. So what do I get when I get that? What's my resultant? Well, let's see. I've got S up here, I've got E bar, and then I have just some meeting point there. Then I've got this F branch, and beyond F I have the retakers, and then the retakers have to pay. And so what I can see by this, and again, try doing this in Venn diagrams, what I can see is that some student has to pay again. Therefore, some student must repay, must pay again. And just one last concluding remark about the conclusions. In fact, we can kind of have fun with this. We can say, well, some student must repay, or some student must retake, or some student failed. Or we can say that someone who is not exempt has to pay, someone who's not exempt has to retake, someone who's not exempt failed. So again, when you flow down and you see what they have in common, you see that they have more than nothing in common. They have something in common. There is at least one member here. So again, when you track that down, as I say, all those various conclusions follow. But again, look at how simple it is. 4 assumptions, a few simple little line diagrams, and voila, you get all this result as your conclusion. Thank you for your attention. Regine, matrique carissime.